All right, section 2.8. This is the last section that we will cover in chapter 2. Notice that we skipped chapters 2.7. We don't do that when it's got to do with elasticity. It's just not something that we're going to cover in this class. 2.8 is called implicit differentiation and related rates. Okay, so implicit differentiation, um, we'll get to that exactly what it means, but what we've been doing is what's called explicit differentiation. So just to make sure you see that there's a difference there. So what we're going to learn how to do is differentiate implicitly, and then we're going to learn how to use that to solve related rates problems. So implicit differentiation and related rates are our vocabulary. Okay, so let's first of all consider the equation y cubed equals x. If we were asked to find dy dx, the first thing you might do is you might take the derivative of both sides of the equation. The problem is you can't do that unless you solve the equation. So we're going to cube root both sides of the equation, as you can see we did right there, and then you can solve that for y. So if we solve this for y, you get y equals x to the 1/3. Take the derivative, dy dx equals 1/3 x to the negative 2/3. We've done that. This right here is what's called explicit differentiation. And the reason it's called explicit is because we could explicitly solve this equation for y first. And then we just take the derivative like we've normally done. So that's going to work really, really nicely when it's in that situation. Maybe we have an equation, however, that looks like this. That one is very challenging to solve for y. As a matter of fact, it'd be very, very difficult to do. So what we're going to have to do here is we're going to have to actually incorporate what's called implicit differentiation, meaning that we are implying that these y's right here, that those y's are still functions of x. So we're still going to basically use the idea that y is a function of x. Because we're doing that, really what we're saying here is that y is f of x. Sometimes you'll see it written as y of x, same idea. All right, if that's the case, this thing called implicit differentiation says what you're going to do is you're going to use the chain rule. You're going to differentiate the function on the left-hand side as if it was just a regular function. You would take the 3 out to the front and reduce the power by 1. But then what you have to do is you have to treat the y that's in this now parentheses right here like it's the internal piece. Basically, it's your g of x of your composite function, or the inside piece. Then you have to multiply the 3y squared times the derivative of y. But we know the derivative of y is y prime, or dy dx. It's written in two different ways here. I don't prefer to use y prime here. I prefer to use dy dx, which is what's in the next step right here. Excuse me. Then you take the derivative of the right side, but the derivative of the right side is x. So the derivative of x is just 1. We know that much, which is right there. So then if I want to solve for dy dx, I just divide both sides by 3y squared. So we get that dy dx is 1 over 3y squared, or 1/3 y to the negative 2. And then dy dx, if we were to rewrite that, could be written as, I'm sorry, it's not rewrite that. You would replace the y with x. So then you would get dy dx equals 1/3 x to the 1/3 raised to the negative 2, and then 1/3 x to the negative 1. Wow, x to the 1/3 to the negative 2 is the same as x to the negative 2/3. And that's only because we could actually solve this right here for for y. So y here would be x to the 1/3 power. All right, it's not as challenging as what I just made it. All right, so let's go ahead and look at this example. Again, it's really not that difficult. Here's the idea. I'm going to take the derivative, we're going to find dy dx for y cubed minus y equals x. You take the derivative on the left-hand side just as if you would take the derivative of anything else, but just remember that because you're differentiating y, and y is a function of x, you have to take the derivative of the y part at the end as the chain rule and multiply it. So the derivative of y cubed is 3y squared, but then multiply that by the derivative of y, which is dy dx. And then minus the derivative of y is 1, but then multiply that by the derivative of y, which is dy dx, and then the derivative of the right side is 1. Now in this case, we want to solve for dy dx, so we actually have to factor the dy dx out, which is what we did here, leaving you with 3y squared minus 1. Then to solve for dy dx, you divide both sides by 3y squared minus 1. Again, it's really not that challenging to do. It's going to become more challenging when you have to incorporate this implicit with your product rules and your quotient rules and stuff. Then you've got to keep it all straight. But the rule of thumb is anytime you differentiate with respect to y, then you're going to take the derivative of that, like normal, multiplied by a dy dx. And this could be for any variable, which we'll see in the next page. So you don't necessarily need to use the chain rule carefully every time you differentiate implicitly. Instead, when you differentiate implicitly, multiply each term by d whatever over dx, replacing the box with the variable you're differentiating. That even includes x's, and you'll see we did that down here. So if we did that, and I'm going to skip right down to here, the derivative of the y cubed is 3y squared dy dx, because the y was the variable, so the y right here would be where the box is up here. And then minus 1 dy dx, because again, the y was the variable here, so that's the one we did. And then even in the last one, the derivative of x is 1, but the variable is x, so it's dx dx. But if you think about it, dx divided by dx, anything divided by itself is 1. So that's what we would get. So you could do it that way too. It's just another way of doing the exact same thing. All right, so let's look at example number 1. And it says differentiate the demand equation x equals the square root of 200 minus p cubed implicitly to find dp d, and in this case it's going to be dx. I think that's actually a typo, so let's go ahead and put that in there, dp dx. Okay, so the derivative of x, that's the independent variable, it's the bottom variable in the dp dx, that's just going to be 1. Now you could write that as 1 dx over dx, or just 1. Now the right side we do have to do, this is going to be a chain rule. So it's actually going to be a chain rule, and then when you multiply it by the derivative of the p part, it's another chain. So let's see, it's going to be 1/2, that's because that's the square root, 200 minus p cubed to the negative 1/2 power. That's the derivative of the outside. Now we have to multiply it by the derivative of the inside, which is going to be negative 3p squared. But then I can't forget to multiply that by the derivative of p, which in this case is going to be dp dx. And that's what we're solving for, is dp dx. Now this is not going to look very clean the way we're going to do this. But you know, we're going to try and clean it up a little bit. So the 200 minus p cubed to the negative 1/2 is going to drop into the denominator because the negative power is going to put it in the denominator. So I know I'm going to have a 2 in the bottom, and then 200 minus p cubed to the 1/2 power. I could have written that as a square root. And then that negative 3p squared here is going to go on top, and then I've got dp dx. So if I want to solve this for dp dx, I can divide by that whole thing, but 1 over that whole fraction is going to flip the fraction. So really I'm going to get 2 times 200 minus p cubed to the 1/2 power over negative 3p squared. That is our dp dx implicitly. Okay, so now let's talk about related rates and how everything that we just did with implicit derivatives goes into related rates. Until now, all of our derivatives have been in the type of d over dx, d something over dx, and have represented rates of change of functions with respect to x. Well, there's going to be a lot of times in applications that we have different variables, where maybe we have something with respect to time, and specifically with related rates, that's what we're going to talk about. So we're going to have d something over dt. And the reason they call it a related rate is because every rate, I'm sorry, every variable changes over time, but they're all related to each other somehow. So let's go ahead and take a look at an example, and hopefully you can follow this. A restaurant supplier services the restaurants in a certain area in such a way that the radius r is increasing at a 2 mile per year at the moment when r equals 5 miles. At that moment, how fast is the area increasing? So really, it's a lot of complicated stuff there with all the restaurants and all that kind of stuff. But really all it's saying is, I've got something which is in a circular fashion. Okay, it's because it's got a radius. And we want to know when the radius is increasing at 2 miles per year at the moment when the radius is 5, how's the area increasing? So we do know that the area of a circle is pi r squared. Okay, now it really should say, I think this is actually, I don't necessarily think that this was worded very correctly, very nicely, but it really should have said that this was a circular area. I'm adding that in. That's the intention of the problem. It was a circular area, because otherwise, how would you know it's a circular area? Um, so what we're looking for now is, how is the area, I'm sorry, yeah, no, how is the area increasing over time? So if we were to take the derivative of this using the idea of related rates, it's still like implicit differentiation in that this is going to be dA dt. That's the derivative of a. It's dA with respect to t. Now remember that pi is not a variable, so it's a constant on the right side. But now when I take the derivative of the r of the radius, it's going to be 2 pi r, because I'm bringing the 2 out to the front, reducing it by 1. But then I have to remember to multiply that by dr dt. So now, because it's a related rates problem and everything is related over time, that's everything's changing over time, this is how you're going to set it up. So dA dt is going to be 2 pi times the radius at that time, which was given to us as 5, times how the radius is changing, which was given to us as 2. I realize that 5 looks like a 15. Again, my pen just seems to drag too much here. So what we're going to get is 2 pi times 5 times 2. 2 pi times 5 is 10 pi, times 2 is 20 pi. So we get that the rate that the area is changing over time is 20 pi, and I guess this is miles per year. Okay, that's the related rate that we were looking for. So again, the general idea here is that a related rate is implicitly derived with respect to time. That's how all this fits together. Let's try one more example. All right, so for Lucci Landscaping, the total revenue and the total cost for the yard maintenance of X homes are given by, and then the two functions are given there. Suppose that Lucci is adding 1 home per day at the moment when the 400th customer is signed. At the moment, what is the rate of change of the total revenue, total cost, and the total profit? Okay, so let's start off with part A. This one really should not be that difficult. Total revenue is given to us as R of X equals 1,000 X minus X squared. Now remember, in this case, it's a related rate. Everything is changing over time. So when we take the derivative, because we want to know what the rate of change is, it's dr dt. And now when we take the derivative of the x's, remember, those are also going to be with respect to time. So the derivative of 1,000x is 1,000 times dx dt minus the derivative of x squared is 2x times dx dt. Now let's make sure we have the information that we needed to figure this out. We are trying to find the rate of change of the total revenue. So let's see, we know that the X value is 400 because we're talking about the 400th. I was getting ready to write DXDT. We need to fill that in. And you know what? There's another typo here. Let's fix that real quick. This should actually be 10 homes per day. I was wondering why there was a zero. I mean, a S on the end of there for 1 home per day. It's supposed to be 10 homes per day. So fix that on your paper. I apologize. But then that tells us that we are changing by 10 homes. So that's got to be 10 DXDT. That's got to be 10 DXDT. So it looks like we're going to get 1,000 times 10, which is 10,000, minus 2 times 400 times 10. 2 times 400 is 800, times 10 is 8,000. So it looks like our DR dt, or the revenue changing over time, of 2,000. And let's see, what are our units here? I think we're in days, so that's $2,000 per day. Yeah, per day. There's the day right there. Okay. All right, so let's go ahead and do the total cost. So the cost function is 3,000 plus 20x. So dc dt is going to be the derivative of 3,000, which is 0. Derivative of 20x is 20, times dx dt. So my cost is changing over time at a rate of 20 times, and again, the change of x was 10 homes per day. So that's going to be $200 per day. And then for profit, we could go ahead and write the entire profit function out, but since we've already figured out what each one of these things changes were at exactly the same time, we can just do that. The profit is going to change over time, and that would just be the revenues change minus the cost change. And we've already figured both of those out. So we're going to get 2,000 minus 200, which is $1,800 per day. And that's it.